Okay, this is lecture 20. This one will not be on the exam. We'll go through the end of lungs. So what we did on Thursday, 20, this from here on out we'll have on the final exam. Your next question is due next Tuesday, the 15th. And let's see what we got. So I'm doing this lecture online right now. It will not be on the second exam. It'll be on the third exam. I got to get your things corrected. I've posted 9 there. 9 will be all the questions on 9 will be fair game for exam 2. So if we're looking at the coverage, here's the exams there. So we got 10 lectures on this exam. So there's going to be probably certainly more than what was on the first exam. We only had 8 lectures. Probably a lot more simple questions on this exam. The final, with metabolism, you're going to have to do a lot more thinking. So I guess plan accordingly. So what do kidneys do? This was a question that was asked to a friend of mine when she was in med school. They were about to study their semester on the kidneys. We're going to do this in one lecture, so we're going to hit the highlights. But the question is, what do the kidneys do? At that lecture, that professor at med school showed this statue here. So this, for those of you that don't know, is David. It's done by Michelangelo. So fairly lifelike, certainly better than I could do. And his explanation was that if you say that the kidneys make urine, you're saying that Michelangelo made David to make wood or marble chips on the floor. So making urine is like marble chips on the floor. The statue of David is like the blood. The kidneys maintain the blood. And the waste product of that process is the urine that ends up in the bladder and gets voided out from there. So the blood is this impressive statue. The marble chips on the floor, the waste product of this process, is equal to the urine. So what do kidneys do? They maintain the blood. So they're going to manage a number of different things in the blood, the solutes, the waste products, the amount of water. Urine is the waste of that process. When we think about the kidney, we need to be aware that there's one way for liquid to come in, 2 ways for it to go out. So we have the renal artery is going to perfuse that kidney. The renal vein, renal meaning kidney, is going to drain the reconstituted blood, the clean blood, the maintained blood out from the kidney. And then the waste product, the other liquid outlet, is going to be the ureter, which is going to have the urine, the stuff that the kidney deems not to be useful to the maintaining the blood. So the extra parts. If we look at the kidney, we're going to look at 3 different layers. So we have the pelvis, that's down where everything comes in and out, this kind of center line. We have the medulla, which is kind of this layer here with the fans. And then we have the cortex, which is the outer layer of the kidney. The cortex is the outer layer of that kidney. So we're going to remember these 3 layers and these 3 inlets and outlets for liquid. So 1 in, 2 out. If we're looking at the cow's kidney, we remember that it looked like that big sack of grapes. This is kind of a flattened out. You remember sort of what we had. Things were much more rounded and covered in fat. So we have the equine kidney over here, kind of horse-shaped. The ox here, the bovine kidney here. And then you've got the, I think it's a goat. No, sheep kidney here, which sort of looks a lot more like ours, But again, you got the 1 in, 2 out on each of these cases, with the 1 being the artery going in, 2 is the vein coming out, 3 is the ureter that leads to the bladder. So same kind of comparison here. We got the equine. This is kind of, in this particular diagram, one continuous cortex. With the sheep or the bovine, we've got this thing of grapes here, and the cortex is discontinuous. Each of the bulbs has its own cortex. Each of the bulbs has its own medulla, the lighter gray on the inside, and each has its own connection to the ureter there. So you've got kind of a different arrangement, but the same net effect. If you compare that, so zooming in on that, you've got an individual lobe, you've got the kind of fuzzy hair look here, a lion, the mane is the cortex, the center gray area is the medulla, and they drain here. We're not showing the blood supply related to this one, but we're draining to the ureter, the waste products that occur. So full page there if you want to take a look more of a look at it. We've got, I think black is the arteries coming down. This kind of shows on the anterior end of the bovine kidney, there's an adrenal gland on both sides. You have one on each side. You have the 2 different there, and you notice that our connections to the blood supply are staggered. We have one above the other. They're not right across from each other, and that makes particularly the artery a lot stronger. If we only have one hole here, not 2 on the same kind of cross section, we have something that's much stronger that's going to resist tearing. So having a branch off and then shortly thereafter another branch off to the opposite side is going to help strengthen that artery. So drawings from the Atlas of Bovine Anatomy. And then here's the full page from the Atlas of Bovine Anatomy with all the keys down here to tell you what all the parts are. So getting back to that generic kind of kidney, we're going to talk about the nephron. The nephron is the functional unit in the kidney. The study of kidneys is called nephrology. So the nephron is what the basic unit of work. So here's a nephron. I think I just skipped over the other diagram there. Oops, and it won't let me go back. So nephron here. So we have a line through here. I guess I should bring out the highlighter. We got a line through here where above this is the cortex, below this line is the medulla, and then we continue on to the pelvis way down low. So we have the nephron here. We start at the glomerulus, Bowman's capsule, proximal convoluted tubule, loop of Henle goes down into the medulla and comes back out. We have the distal convoluted tube. So the distal versus proximal is the adjacentness to the Bowman's capsule. Proximal is earlier in the nephron, distal is later on. And then we have a collecting tubule that connects to a number of different nephrons. So each of these points here would be a collection point for another nephron. So nephrons collecting, branching, and then we're going to combine these until we get to the single ureter leaving the kidney. So the nephron sits in our kidney like this. We got the first part here in the cortex, loop of Henle down below, distal convoluted tubule, collecting tubule works its way into the medulla and then to the ureter, which sits in the pelvis. So zooming in on this, we have a capillary bed, an artery comes in, we form a capillary bed that's completely enclosed around this bed by something called the Bowman's capsule. And this is where the filtration system starts. We split the blood into basically just red blood cells, some big proteins, and just enough water to keep it moving so we have a sludge. And then all the plasma is filtered out into the Bowman's capsule and begins its journey through the nephrons, the proximal tubule, loop of Henle, distal loop, or distal convoluted, and then collecting tubule. So proximal convoluted tubule goes into the medulla. We got our loop of Henle. That's going to go back up to the cortex, down and back. Then we get to the distal convoluted tubule, and then we drain into the collecting duct or collecting tubule that's going to keep branching or merging till we get down to the ureter. So this is a more probably accurate drawing, but a little bit more complicated. So again, we got the Bowman's capsule, proximal convoluted tubule, loop of Henle down here, thin on one side, thick on the other, distal convoluted tubule, and then the collecting duct with multiple nephrons connected to a common collecting duct as we go through the medulla of the kidney. So a bigger diagram for that, you can print that off, take a better look at it. Now the Bowman's capsule is surrounded by another capillary bed. So you're coming out of the arteries in here. You got your first capillary bed here, the glomerulus in the Bowman's capsule. Then we go together and we got the sludge moving out into a capillary bed that's going to surround each nephron. So one capillary bed, two capillary beds. Once we've gone through that, we now have the veins, and then we're working our way back to the heart. So interlobule vein, and that's going to go eventually to the vena cava, back to the heart. So that is very intimately connected to the nephron, and the movement of liquids, whatever we filtered out into the nephron's going to decide what gets put back into this capillary bed and becomes that reconstituted, that clean or maintained blood that goes back to the heart. So you're looking at 20% of the blood flow is going to go through the kidney. It's going to be filtered through the nephron. The kidney will decide what stays, what goes. And then half or a portion will go down the collecting tubule to the ureter, and a portion will be returned to the blood, which goes back to the heart. So same diagram here, a little bit bigger detail in your handout. So we want to talk about the function of the nephron. So to make it a little bit easier to understand, what I've done is kind of pulled that nephron and laid it out flat. So we got the glomerulus in here, we got it surrounded by the Bowman's capsule, BC, proximal convoluted tubule, loop of Henle, distal convoluted tube, collecting tubule, which is going to drain into the bladder. Whole blood is going to come into this first capillary bed, the glomerulus, and then we've straightened out and combined that capillary bed that normally surrounds the nephron, and we've kind of pulled it out and laid it parallel. So once we get down here, we're going to head back through the arteries to the heart. So whole blood comes in, glomerulus, we split pretty much plasma here with sludge, with cells, a bit of water, some of the bigger proteins that can't be filtered. They're all going to start moving down here. All the salts, the water, the smaller molecules, the waste products are going to be moved in pushed out of the glomerulus, collected by the Bowman's capsule, and begin their journey through the nephron. And what we're going to have is everything that's of use to the body or needed by the body is going to be transferred from the nephron back to that vasarete capillary bed that surrounds the nephron. So the nephron is going to identify things that, oh, we need sodium, we need glucose, we need amino acids, we need no, we don't need urea. Things that we need, and they're going to be put back. And then hopefully by the end, we have reconstituted blood. Whatever does not get taken back and transferred back to the capillary bed is going to end up as urine at the other end. So we have the solutes that are needed are going to be recognized by the nephron and pulled out actively and moved back to the blood. So we start moving our solutes across, and then water is going to follow passively. So water follows solute. The nephron moves using energy and enzymes and transporters, things back to the blood, and then water is going to get there. So by the end of that capillary bed, you've got that reconstituted blood that has been cleaned of all the excesses that need to be removed. So we're looking at this more in situ. So as things leave the nephron going down here, the loop of Henle, they're going to transport over to the nearest spot on the capillary bed that they can, so going this way, going that way, so they can be absorbed and put back in that capillary bed. So by the time we get to here, we have reconstituted or cleaned blood. So let's think about this when we're messing with our friends. So I have a friend, Paul, that got his hands on an antibiotic called rifampicin. And one of the side effects of rifampicin is it turns bodily fluids a bright orange red. It will also, kind of color the eyes, tint your spit, all that stuff. So if you're not warned about this and you go to the bathroom, you're going to look like you're pissing blood. That can be very scary if you're not prepared for it. So Paul wanted to mess with our friend Vern. We're going on a camping trip, and Paul comes up to me and he goes, "We need to get Bill to eat this." And I was like, okay. So me and Paul put our heads together and we said, I got an idea. So he had this stuff all crushed up, little fractions of a pill or whatever. We put it in one side of a chocolate covered donut. And I walked up to Bill, who loves a challenge, or Vern as we call him. Bet you can't fit this whole donut in your mouth. So I took the donut and I forced it in his mouth with the antibiotics going in first, and then because it was a chocolate covered donut, the crunchiness of the pill was sort of hidden by the crunchiness of the outer shell on the donut. So we left the house from there, and then we went out hiking. This was a January hike, so we were out in the snow, tramping through the woods on the Appalachian Trail, and we got to our lean-to where we were going to stay for the night, and nature called, and Vern, AKL Bill, had to go relieve himself behind the lean-to. So he gets back there. Me and Paul are just giggling because we knew what was going to happen. And, there's snow there, so the effect is even more dramatic. So he starts screaming, "Hi, hi!" Something's not right here. And we're laughing our asses off because of what's happened. So unbeknownst to him, Bill, he thought he'd ruptured his kidney. He had fallen earlier, slipped in the snow, and landed on a tree. So this kind of fed into that. So we explained to him that no, it was just a prank and being Vern, he goes, "Oh, that was so cool. You got me. You got me." So, anyway, so how does this fit with kidney stuff? If we're thinking about that antibiotic goes to the kidney and gets filtered out. It's in the nephron. The nephron does not recognize it as anything important. It does the same thing with penicillin, but penicillin doesn't have a color to it. So once that stuff goes to the kidney, that's why we got to take antibiotics multiple times a day, is the kidney filters it out very quickly because the nephron goes, I don't know what this is. I'm not going to deal with this. Let's get rid of it. So it doesn't actively move it from the nephron back. It's considered unidentified and becomes a waste product in the bladder. And that's why you get, because it has that orange red color, that's why it turns your pee very bright red. So if we're getting a little bit more scientific, there's a diagram here. We talk about stuff leaving through the kidneys. So kidneys is responsible for removing a number of different things. We can lose hydrogen ions. We can lose organic acids and bases. We can lose ammonium. And each of these areas has specific responsibilities. So the cortex, we look like we're getting rid of some, electrolytes here. As we go down through the loop of Henle, we're dealing with ammonia and urea. Ammonia and urea, we need to get rid of those. And then as we get down here in the collecting tubules, we got potassium, hydrogen ions, and ammonium. So things that are going to be secreted or managed in certain areas, they're going to be pushed out through. We're not going to ask you to remember which ones go where, but just realize that there are specialized regions that are designed to get rid of specific things. So making sure that these things get put into the nephron. So in the opposite direction, things that are saved by the kidney, we have bicarb, we have water, urea, we've got electrolytes, sodium, potassium, we've got some acids, magnesium, calcium, and chloride are all going to be resorbed and put back in the blood by the nephron. The nephron recognizes all these things. We're going to have a lot of management of water and sodium and chloride in the loop of Henle. And then we get over here, we're going to have a lot of ions that we have to deal with over here. And then as we go through the collecting duct, water is going to be extensively managed. Urea and magnesium are recognized and can be brought back and then ultimately put back in the blood. So that's that diagram where it's plus is reference where you get it. So what gets secreted actively by the nephron, what gets pulled back actively by the nephron. And if we think about this part here, I forgot to mention this, you got the glucose, you got amino acids, you got all the things that are small but are recognized by blood. A lot of that stuff is going to be taken care of by the nephron, and it appears by this diagram to suggest that it's the proximal convoluted tubule that moves all this stuff back to the blood. If we're looking at the osmolality of our nephron, we're going to start out with, we're going to filter out that plasma. We're going to be somewhere near isotonic, so 300, 300. As we go into the medulla, we're going to have something that's increasingly hypertonic. This is suggesting down here 2400 milliosmoles. The loop of Henle is going to mimic that as it goes through. So water is going to be pulled out all the way here, and the solutes remaining on the way down. So we're going to have a concentration of those solutes, and we're going to increase the osmolality. As we go up, we're going to manage our sodium and chloride, particularly with this plus here. Stars are where we move those sodium and chlorides. These two sodium and chloride places are going to be under the management of aldosterone, a hormone that helps us with our electrolyte balance. You got water coming out, and then going down through here, we have a hormone highlighted in yellow called ADH, antidiuretic hormone, or it was sometimes called vasopressin. So synonyms, all three of those. And antidiuretic hormone will open up this collecting tubule and let water flow out. If that hormone is not present, the water will continue to flow through the collecting tube and you'll have lots of volume of dilute urine. If ADH is here and opens this collecting tube, you will allow that water to follow solute and therefore concentrate this urine to a much higher osmolality. So having that move out, water move out, will give us concentrated urine versus dilute urine. So you have that diagram there. I've highlighted some of it to make it a little bit easier to follow. So this is showing your nephron here, very simplified. We're coming down here, the loop of Henle, we're going back up, and then we're going into the collecting tubule, and then we've got the Vasariti, or Ricky, the papillary bed that we're dealing with. So you have something that's going to take water and sodium chloride in and become more voluminous as we go through, as we head back to the artery here. So it's also going to have water and electrolytes are going to move back into the bloodstream, be collected, and hopefully the blood at the other end is cleaned and reconstituted. So this illustrates what happens when we have no antidiuretic hormone. Water becomes impervious to this collecting tubule, this downward thing, so we get a large volume of hypotonic urine. If we have ADH present, we open up that collecting tubule, and as that osmolality increases, we're going to have a strong drive to pull water out of that collecting tubule, and we're going to get a small volume of concentrated hypertonic urine. So this would be if you're working outside in the summertime, and when I used to do bales, I was a stacker of bales in the haymow at my dad's place. You're getting up into that haymow. We had a black slate roof on that barn. There was a lot of heat in the summer, particularly when you were loading hay at the end of the day. On that roof, there's a lot of heat. So we do a wagon. One of my dad's employees, Mark, would be, he was the fastest at unloading the wagons. He would throw stuff on the conveyor. They would come off the conveyor. My dad would bounce it across the barn to me. And then I'd stack everything at the other end with the, all the things there. I got to be able to walk over the stack without falling in. So everything had to be tight. Everything had to be such that, you couldn't slip a foot in anywhere. So, you're stacking hay on days when you're looking at the weather forecast is like, it's going to be one of those Triple H days, hot, hazy, and humid. You shouldn't be doing physical labor outside, So, okay, I was doing heavy physical labor inside, sweating like crazy. We'd do a wagon. I'd run down to the milk house. I'd drink as much as I could, and then run back up and keep going. Because while I was running downstairs, Mark was bringing in the next load, and he's pretty good at getting that and gets the bales going. So we're trying to get things done as quickly as we can. I'd be drinking many gallons of water as we were unloading those things, wagons, and stacking those bales, but I wasn't producing any urine. So you knew on a day like that, since I was losing so much water through my skin, I had a lot of ADH. That means I was being my collecting tubule was being open, so all the water that went to the kidneys was being conserved and brought back. So it could be used to sweat, it's used to keep my blood volume up. So we had a lot of different things happening there, but I was drinking a whole lot of water and not producing really any urine at all. So ADH was certainly dominating my system as it would with anybody in that summer heat. So thinking about that, this collecting tubule coming down, we've got the organization there, and depending on where we are and what we're doing, we'll produce a lot of urine or a little urine depending on the needs there. So again, ADH, water follows solute. Without ADH, water does not follow solute. So this is one of the exceptions. The rumen lining is one. Water does not follow solute. And this is another exception. The collecting tubule of the kidney, water does not follow solute. So we're looking at these diagrams here. This talks about the influences on the kidney to either reduce water secretion or reduce sodium secretion. And there's a lot of things involved here. We're not going to get into too much detail, but you can follow it if you kind of pick one point and kind of work through. So ADH is secreted by the posterior pituitary. It flows through the blood, acts at the kidney collecting tubule. So the reasons to secrete ADH will be, you've got high osmolality is going to tell the posterior pituitary to conserve water. You've got osmoreceptors. If you've got excessive amounts of solutes in there, so this is where part of where the hypertonic saline would work. You've got low arterial pressures. If you get those, they're going to increase ADH to conserve water to get that back into the bloodstream and try to get your volume up. So if you've got thirst due to low water intake, or you've got too many electrolytes with the hypertonic saline, that's going to drive the thirst receptors, which is going to tell the brain to drink very, very quickly. If you've got low sodium intake, you'll get salt hunger. Salt hunger will go to here. Again, ADH will go to ACTH, adrenocorticotropic hormone. That's going to go to the adrenal cortex in front of the kidneys. That's going to secrete aldosterone, and that's going to have negative impact on the sodium secreted. So if we don't have enough sodium up here, salt hunger, things like that, the kidneys are going to be told, hey, you need to conserve some sodium and save it for later. So bring it back into the kidney, put it back into the bloodstream, try to get it built up again. So we'll talk about aldosterone a little bit more, ACTH a little bit more when we get to the endocrine system. So what do kidneys do and how do they work? So I hope this gives you an idea of what's happening. Again, you get into the details. I've got a 30,000 foot view here. You get into the details, it can be really complicated as how osmolalities work and what moves where and how stuff moves. And I didn't really fully understand how the kidney worked in a detailed sense until late grad school, about my fourth or fifth physiology, where they really dug into the kidneys and showed how all those things are managed. And it's really complicated, but we're going to keep it simple here, the basics on how blood is maintained. So we're thinking about that hypertonic saline there. We know that water intake is determined in our cows by dry matter intake, milk production, and the third thing that the National Research Council says about dairy cows is that sodium has a real driver of water intake. So if you're thinking about sale day and maybe a little salt in there might encourage a little bit more drinking right before they go into the ring. You've got increased osmolality in the blood. That's going to drive the thirst receptors to go there. But with a hypertonic saline, we're doing that through an IV. We're putting in more electrolytes, sodium and chloride. So we're thinking about hypertonic saline for environmental mastitis. So that hypertonic saline is going to help us clear the body of the bad things that are as a result of environmental mastitis. So leukocytes, the white blood cells, are going to destroy the bacteria. When they do that, they engulf those bacteria and destroy those bacteria. And in doing so, they release parts of the bacteria that are going to elicit effects from the cow and get them in very depressed, very feverish, very lethargic, things like that. So you have all these parts of bacteria that are released into the bloodstream. We need to get rid of those, and the kidney is going to be responsible for getting rid of those. So we put that IV in. We put a lot of electrolytes in there. That is going to hit those receptors in the brain, those thirst receptors, and say, drink. And we can see very dramatically, 5-10 gallons disappears very quickly with these cows. And that increased drinking is going to flood the system with water, and then the kidneys are going to, we got way too much water in here. We got way too much salt. We got to get rid of this stuff. We don't need all this stuff. So that increased drinking is going to lead to a higher turnover in the body with water, and you're going to flush out the system as the kidneys go, well, we got way too much water in here. Let the water go. Let the electrolytes go. And with it, you're going to have the bad things that have been released are going to be flushed out as well, because the network goes, I don't know what to do with bacteria parts. Just let it go. So that gets all the system flushed out. 10 gallons of water. You're looking at, something that might start to approach a lot of the water volume in the blood, like 50% or something like that. So you got to flush it out. So the more water that gets flushed out, the more likely we are to take those bad things out with the nephron and get them into the bladder and out of the body. So we can get rid of those fevers. We can get rid of that lethargy. We can get rid of that kind of depressed kind of outlook and look. Get rid of those endotoxins, the bad things that are released when the bacteria are destroyed. So we're looking at our parts of the bacteria. They're going to get filtered out, the endotoxins, and the nephron's not going to know what to do with them, so they're going to end up in the bladder. So the more water we have going through the system, the more that gets flushed out, the more endotoxins get pushed out into the bladder. We could do the same thing with a saline IV, just getting more volume in there. You could probably do the same thing pumping the water, but it's a whole lot easier just to give a hypertonic saline and let her do the management, let her do the drinking, instead of this. I mean, I've sat there with a cow with a 5-gallon saline solution dripping through, and they're going through a 16 or an 18 gauge, or I think we used 12 or 10 for IVs at Michigan State. It still takes a long time to go through that. So this is something you can do in 10-15 minutes, and then let the cow do the work of getting flushed. So I got to get this posted at some point. Talks about that oral therapy, fluid therapy for cows, getting them back, getting them rehydrated. So let's go back to the blood for a minute. Normal blood values, we have, now that we've talked about the kidney and the lungs, we can bring things together here. Normal pH of the blood is about 7.4. It's going to range a couple hundreds in each direction, or so 7.38, 7.42, somewhere in there is a normal range. We have bicarbonate ion, normal value is 24 milliequivalents per liter. And then the partial pressure of carbon dioxide in the blood, we've shown that most of the time, except the stuff going back to the lungs, we're at 40 millimeters of mercury. So that's our partial pressure. Blood pH is controlled by the lungs and the kidneys. So we have those two things working in opposition that are going to help keep it around that 7.4. The lungs are going to have quick control. They're going to control carbon dioxide. And the kidneys have more long-term control where they set levels of, okay, this is how much bicarb we're going to save, how much we're going to let go as we move blood through the kidney. And to quantitate this or express this relationship between the lungs and the kidneys, we're going to use something called the Henderson-Hasselbalch equation. So blood pH is determined by the amount of carbon dioxide in the blood and the amount of bicarbonate in the blood. And the Henderson-Hasselbalch equation shows the difference between the two, or connection between the two. So you've got carbon dioxide and water. We assume water is in infinite excess. This is limited in some level. We have carbonic acid here in the middle. It's an unstable intermediate, so it's always going to go this way or this way. It's not going to stay this form for very long. A carbonic acid is going to dissociate into a hydrogen ion and a bicarbonate ion. So these are key reactions in the lungs, kidneys, and rumen. So if the lungs control the carbon dioxide, the kidneys control the bicarb at the other end. So pH is determined by the Henderson-Hasselbalch equation by carbon dioxide level controlled by the lungs and followed by bicarbonate controlled by the kidneys. The lungs control the partial pressure of carbon dioxide. We can hyperventilate to decrease our hydrogen ion concentration, or increase our hyperventilate to decrease the partial pressure of carbon dioxide, or hypoventilate to increase the partial pressure of carbon dioxide. And then this has downstream effects. Decreased carbon dioxide is going to lead to decreased ions, which is going to lead to an increased pH. Hypoventilation is going to increase the carbon dioxide, which is going to increase the hydrogen ion concentration, and then that's going to decrease the pH. Kidneys are going to work at the other end of the equation, the right side of what we did, and with the bicarbonate. So they're going to increase, resorb, the nephron's going to put back bicarbonate into the blood if we want to increase bicarbonate, and it's going to let it go down to the ureter, to the bladder, if we want to decrease bicarbonate in the blood. So if we increase bicarbonate, we're going to shift the equation to the left. That's going to decrease the hydrogen ions, which means the pH will increase. If we let it go, we get rid of it on the right side. We're going to shift the mass action. We're going to create more hydrogen ions, and that's going to decrease the pH of the blood. So all these different mechanisms are going to combine together to balance out the blood. So we look at mass action. If anybody's had chemistry, we know if we add reactants on this end, it's going to push the equation this way. If we add reactants on this end, it's going to push the equation this way. Everything goes back to equilibrium. If I take carbon dioxide away over here, that's going to pull bicarbonate and back this way. Mass action will go this way. If I remove bicarbonate, mass action is going to go to the right, shifting things there and influencing our hydrogen ion pool, which determines pH. If we're thinking about mass action to reduce the number of hydrogen ions present, to increase the pH ultimately, how does that happen? We can think of it as building piles. We're making things bigger, or making the pools bigger. Not like a tilting seesaw where we're putting stuff on and things tilt the opposite way. We're making piles. So let's illustrate that. So we're going to make some piles here. So we're going to do some mass action. We're going to try to decrease the carbon dioxide. This is going to get smaller, or increase the bicarbonate, make this bigger. That's going to make the equation run this way. So that's going to steal hydrogen ions, reduce them, and increase the pH. So either we have to increase our bicarbonate to make that happen, build this pile, or reduce this pile over here to get the equation to run this way. So by reducing those hydrogen ions, we're moving the equation this way, either by getting rid of this or building this pile over here, and everything runs downhill. That reduced hydrogen ion concentration is going to lead to increased pH in the blood. We reverse it. How do we increase hydrogen ion concentration? We want it to move this way. So we have to build piles or remove piles to get the equation to tilt this way. So we increase carbon dioxide over here, or decrease bicarbonate over here. So increased CO2, decreased bicarbonate. We're going to run the equation this way, and that means we increase our hydrogen ion concentration, which means we lower the pH. So by controlling the CO2 or the bicarb, we can control the amount of hydrogen ions and therefore the pH. Okay, another advantage or disadvantage of the Henderson-Hasselbalch equation, as we alluded to in the last lecture, is that it will influence the ability of the blood to move carbon dioxide. So we know that increased hydrogen ions will make the heme less sticky to O2 and make it drop the O2 wherever it might be. If you remove hydrogen ions, the heme gets more sticky and the oxygen sticks better to the heme. So where are we increasing our hydrogen ions? We're doing that out in the tissues where we have active production of carbon dioxide. Active working tissues will produce more carbon dioxide. This will build up, and then we'll generate more hydrogen ions locally, and that's going to make the heme less sticky of our oxygen. So you have now a mechanism that where the body tissues are working the hardest, that's where this oxygen is more likely to get dumped. So hard-working tissues are going to generate a lot of CO2, which means a lot of hydrogen ions, and they're going to dump a lot of oxygen there to help foster that that high metabolism in that local area. If we go to the lungs, we get rid of CO2. That's good. Excuse me. That's going to reduce hydrogen ion concentration. That's going to mean the heme is more sticky and more likely in the lungs to pick up that O2. So we tend to have heme very sticky for oxygen in the lungs. So we pick it up very quickly as we get rid of the O2 in the lungs and the O2 in the blood. As we generate that out in the tissues, we're going to have the heme dumping that oxygen so that the oxygen is left to the tissues that need it the most. So I think that's the last slide in this set. Hopefully you'll have a chance to review it before April 15th. We'll see you in class.